Thanks, everyone. Thanks for joining this session with everyone of us over here. And I'm very glad to come back to Coxine, although virtually this time. Today, I'm going to present a paper called Information Sampling in Correlation Judgment. And this is joint work with graduate student Xiumei Zhang and my former postdoc advisor Sudeep Patia. And so to give you a little bit of background of this project, so the big background is computer graphics. As you may know that computer graphics has been increasingly popular in the last few decades, I believe, for statistical communication and decision aids in a number of domains. Here I use an example here for climate change. For example, Howard et al. In 2016 highlights the use of computer graphics for communication in terms of climate change problems, and they actually make a pretty big emphasis on the cognitive side of this process. On the right side, you can see there is a copy of the graphics on the left side, but as you can see, some regions of this figure is blurred, and that's based on the eye tracking data they collected from non-expert people in viewing this graphic. And that's the background. And here in this paper we focus on a specific graphic called scatter plots for displaying bivariate relationships. And here's an example to show how powerful scatter plots looks like. So if you look at the numbers, right? So on you look at x1, y1, x2, y2, etc. And you may find these numbers are pretty messy, and you cannot find out a clear pattern over there. But if we display those two variables in a 2D scatter plots like at the bottom over here, is pretty straightforward, right? So I believe many of us have been using and have been reading scatter plots a lot in our research as well. And despite the huge convenience that scatter plots brings us, actually we people still have a number of judgment biases in terms of reading information from the scatter plots. And the very robust effect is what is usually called underestimation. And that means, when we read information or bivariate correlations between two variables from those plots, we constantly underestimate the correlation from the data points which were displayed on the graph. So on x-axis, you can see a number of different presented correlations, and on the y-axis, you can find that the estimated correlations by human participants. And as you can see, most of these data points are below the diagonal. So people constantly underestimate the correlations, and this does not the education in statistics doesn't matter, because undergraduates in stats class and psychology class almost doesn't differ over here. This comes from some very classic early research. And of course, there are other aspects of behavioral biases in such judgment, like different aspect ratios. And there are a number of others which I don't mention over here. But the big idea is we make biased judgment from those visual inputs. And there has been a number of different theories to account for those biases, mostly focus on the geometric properties of this graphs, right, of the data points in the graph. But the theory that we are particularly interested in takes a slightly different angle. We take I call it a more cognitive angle. So we basically assume people sample information from the graphs, which is pretty straightforward. That is what everybody of us do every day, right? And then we sample information from the graphs, and then we learn from the graphs. And then finally, based on this learning process, we make judgments. And so in in terms of operation, we do it this way. So in terms of capturing participant sampling process, we use eye tracking to capture what data points the participant has seen in the graph. And then we assume that participant may be able to perform some mental regression as in a simple regression, right? So so here is some more concrete examples of how we do this. So here's the visual input part. Let's take a very video clip. Right, this is a video clip about the fixation trajectories while they view the scatter plots in 3 seconds. And we assume participants are Bayesian learners who are interested in updating the properties of this regression, right? This bivariate relationship, and in particular, they are interested in updating the parameters of this regression line, which consists of 2 components, which like theta 0 is the intercept and theta 1 is the slope. And this update is based on the observed data points they have they got from the graph. Here we have x coordinate and the y coordinate of these data points in the graph. And this is pretty straightforward standard-based rule, and participants may be able to get the resultant theta after observing a subset, maybe not all of the data points, but a subset of the data points, right? And so we can get a posterior estimation of theta 0 and theta 1. And in particular, theta 1 is important because we know that we can calculate the Pearson's correlation from theta 1 based on the observed standard deviation of the x-axis and the y-axis. This is the Bayesian learning model. So that's the theoretical setup. So we tested this theory in 2 experiments. We have actually additional experiments, but in this talk, I'm going to focus on 2 of them. The first one focuses on underestimation, which is one of the most robust estimation biases in reading correlations from scatter plots. The stimulus are pretty simple. We generate a total of 40 scatter plots, ranging with correlations ranging from 0 to 0.9. So there are 10 different correlations, and within each correlation, we have 4 repetitions that generates our 40 scatter plots for us. And the procedure is pretty standard. Each try starts with a 2-second fixation, followed by a 3-second viewing of the scatter plot. And after that, the participants make a self-paced judgment of the correlation in the scatter plots. And that's the procedure of the trial. And here's the results of the study 1. So we have 2 sets of estimate. We can estimate. We can get the estimation bias in 2 ways. One is the actual estimation bias, which is calculate the subjects estimated correlations over here, and minus the actual correlation, we can get an actual estimation bias. That's the actual estimation bias, and we find that consistent with existing literature, participants show an underestimation bias. But even more interestingly, we find that the Bayesian learning model, which is trained by the eye tracking data, it can also predict an estimation bias in terms of judging correlations from scatter plots. Although the magnitude of underestimation is different, significant in this case, but the direction is the same. And we also evaluate the predictive accuracy on the trial level of the Bayesian learning model. So on the x-axis over here, we have actual bias for each stimuli. So on there are 40 data points over here that represent they represent each of the 40 scatter plots. And on the y-axis is the predicted bias by the Bayesian learning model on each of the scatter plots. So on the trial level, we show that the model can predict estimation bias pretty accurately. And that's study 1. And in study 2, we introduce a new variable, which I call, let's say, call it a display format. So we introduce 2 different display formats. One is the landscape, the other is portrait. Here are 2 examples of these 2 conditions. So in the landscape condition, the x-axis is longer than the y-axis, and in the portrait condition, the axis is shorter than the y-axis, and that's the only difference between the 2 conditions. And other than that, the procedure in study 2 is exactly the same with the study 1. And then again, here's a overview of the group level results. So for the actual judgment bias, we find that in both conditions, participants underestimate correlations, right? But also we find that the underestimation bias is stronger in the landscape condition than in the portrait condition. And this is consistent with existing literature as well. So this is not surprising. But the more interesting thing is that the Bayesian learning model that are trained simply using the eye tracking data in the free viewing page, we find that the Bayesian learning model can also predict this underestimation as well as the asymmetry between these 2 conditions. That is, the underestimation bias is stronger in the landscape condition than in the portrait condition. And then we also evaluate the trial level accuracy of Bayesian learning model. We also again find a pretty strong predictive accuracy at the trial level for the Bayesian learning model. So far, we have seen that the Bayesian learning model using the eye tracking data can successfully predict participants' underestimation bias and some asymmetry between conditions in study 1 and study 2. And the next step we want to do is to see how participants move their eye, move their fixations over time, right? To do this, we, for example, we do this for the horizontal axis, and we divided the horizontal axis into 10 different sub-segments or bins, right? So basically, using this segmentation, we are able to model the eye movement along the horizontal axis as a multinomial logit property. And then we write the activation of each bin over here from H1 to H10 as a function of 4 different variables. The first variable is position, which indicates whether the bin is on the left side or the right side of the screen. And the second one is the distance variable, which indicates whether the distance from the next fixation to the previous fixation. So that measures how, whether you want to search a proxy mode data point or a distant data point. And the third and the fourth predictors are 2 statistical properties. The third one is pretty straightforward. It means the density of the data points in the graph. So we generate this data, all the data points from standard normal distribution. So we can calculate the density of data points for each bin very simply. And the fourth variable is called expected information gain. And I'm not going to details, but this is related to the optimal design, experimental design, in terms of choosing the right or the most informative data points for regression. So we can calculate this expected information gain for each bin and put it here in the regression. And with this model setup, we estimate those parameters beta 1 through beta 4 under a hierarchical Bayesian framework. And for both studies, we find that we find positive beta 1, which means that participants have a right side bias in fixation. And we have a negative beta 2, which means people tend to search for proximal data points rather than distant data points. And we have positive beta 3 and positive beta 4. That basically means we are sensitive to the statistical properties, right? And as you may remember, in study 2, we have two conditions. We have a landscape condition and a portrait condition. And we can compare whether there is some difference between these two conditions, right? And here I'm going to focus on beta 3 and beta 4. So basically, we find that beta 3 and beta 4 are not significant different in these two conditions. So in that sense, I think we can, like cautiously claim that, participants are equally sensitive to the statistical properties in these two conditions. And then for the vertical axis, we can do the same thing. We divided the vertical axis into 10 different segments. And we model the vertical transition in a similar way as we did for the horizontal axis. So we have three variables. The first one is position, which indicates the bin is the upper side or the lower side of the screen, and the second one is the distance, which is similar to for the horizontal axis, the distance to the previous fixation, and finally is the density of data points in beta 7. And we again use hierarchical Bayesian estimation. We find positive beta 5, negative beta 6, and positive beta 7, which are not so surprising. And again, in beta 7 is the statistical property. We don't find a significant difference in these two conditions, but we do find some significant difference in beta 5 and beta 6 in study 2. So overall, we have two key messages to show over here. First of all, we propose that biased information sampling actually may give rise to biased correlation judgment from scatter plots. And we've in our in-depth analysis of the eye fixation data, we find that the two key elements in information sampling process. One is the statistical properties, and the other one is our information sampling from scatter plots is also influenced by the display format. And that's all about the talk. Thanks.
Thank you, Lisheng. We have about 3 minutes for questions. Go ahead and type into the chat if you're on Google, or use the microphone in the room if you're there in person.
Thanks, Leah.
All right, I've got a question from Vijay Marupudi. What do you think of the possibility that participants are sampling more than the eye tracker captures due to peripheral vision? Any thoughts on how to account for that?
Yeah, thanks, Vijay. That's a really good question. At the beginning of the project, we did have struggled a bit over here because that's true. So not only the information in the central vision enters our brain, right? What we do is we end up doing something of a weighting scheme in terms of the sample data. We do not make a circle and just use the data in that circle as the input, but we find the central vision vision, the position of central vision, and use let's say weighting scheme which is proportional to the distance. The weight is inversely proportional to the distance to the central vision point, and use that way to account for this this potential effect of peripheral vision. Yeah.
Hi, great talk. I have a question, a related question. So in the visual search property slide, used 4 variables. I'm just wondering, like, what are other possibilities and heuristics, and why do you choose these four in particular?
Yeah, that's another great question. Yeah, primarily I was mostly interested in beta 3 and 4 because I think that may undermine a lot of judgment biases. But we met a number of problems when fitting it this way because we find that this one the expected information gain has a pretty unexpected negative effects, and it's very weird. So we find out what is going on. We look at the data. Firstly, we find there is a pretty strong position effect when we look at the left and right side, and we decided to include this one because the card is it's interesting. It's 0.5. It's just in the middle of the screen. So I decided to include position, and the distance. The distance is a good way to explain why this is there were a negative effect of expected information gain because people have a strong tendency. I'm not sure. I think there is still space for discussion. What to include, what to exclude. But that's the way it get here.